we're going to start talking about acids and bases. And so I just want to review naming each of them. And so there are four substances here to name. We'll look at naming each one of them, briefly review how to tell it's an acid and a base, but you'll get more into that during the video today. So for number one, name the following substances. So when you're looking at naming, you always want to pay attention to what you have combined. So here we have hydrogen combined with SO4. So I'm going to kind of put a dotted line down. Whenever you have hydrogen at the beginning, so hydrogen at the beginning, like in number 1 and number 3, that tells you that it's an acid, because acids and bases are named differently. With acids, when you have a polyatomic, like SO4, it's going to be named differently than if you just have a single element like Br. So, SO4 is what polyatomic ion?
Sulfate.
Sulfate. All right, so SO4, I'll just write up here, SO4 is sulfate. And so when you name an acid with a polyatomic ion, you change the ending. So you just change the ending and then you add acid at the end. So again, we know it's an acid because it starts with an H. The way that when I taught honors, the way that we went through it is that 8 changes to ick. So you ate something icky is always how I taught it. So the 8 ending changes to ick, and the ite ending, so like nitrite, sulfite, changes to us. So you can remember I and us, you ate something icky. Now some of these polyatomics you might have to add a little bit to. So sulfate actually becomes sulfuric acid. So sulfate 8 becomes ick. Because it starts with an H, we add acid at the end. So H2SO4 is sulfuric acid. I'm going to skip down to number 3 because that's an acid. It starts with an H. So we know we're going to have acid at the end of the name. When it's hydrogen and a single element, Br, Cl, I, F, right, S. You have hydrogen and a single element. You need hydro at the beginning. Now think about like HCl, right? Use HCl as the example. What's HCl? Hydrochloric acid. And we use HCl all the time. HCl is hydrochloric acid. So when it's hydrogen and a single element, you start with hydro, then you put the beginning of the element. So Br is bromine, and you end it with ick, hydrobromic acid. So I always say when it's hydrogen and a single element, that could be something like HBr, H2S. H2O is water, so that's different. Or you can do like H3N. It's still hydrogen and a single element. You have hydroic acid. Something like HNO2. NO2 is nitrite. So HNO2, because NO2 is nitrite, it's a polyatomic ion. Ite goes to us, becomes nitrous acid. So that's naming acids, just so that if we see a substance in an example, we're able to name it. Now bases are named just like ionic compounds, because it is. Bases are ionic substances. Metal and a polyatomic. Metal and a polyatomic. With the exception of ammonia, which is NH3, a lot of bases that we work with are just ionic substances. What's Ca?
Calcium.
Calcium. And then what's OH? Hydroxide. So for number 2, right, CaOH2 is just calcium hydroxide. NaOH, sodium hydroxide. Right, so LiOH It's lithium hydroxide. Now, the only time you have to be careful with naming, and this is going way back, is if you have something like FeOH2. Fe is iron. Iron's a transition metal which can carry more than one charge. So you have to make sure to put Roman numerals if you're dealing with a transition metal. But again, this is just to make sure that as we work through, if we see sulfuric acid, we know that it's H2SO4. Right now, you'll be able to watch. Then we'll go through examples, answer questions, both conceptual and there will be some math examples as well. So before we get into examples, I want to do a review of acids and bases. So on the document camera, I have two substances, and I'm going to not quite tip them over completely because I don't want them to pour out. I have HCl and I have NaOH. So one of the questions from the video was about the Arrhenius definition. And it was, do acids always start with H and bases end with OH? Yes, if it's following the Arrhenius definition, an acid produces H plus in solution. And so that means that it has to start with an H plus. So HCl follows the Arrhenius definition. It starts with an H, meaning it's going to produce H plus in solution. Now, sodium hydroxide, right, NaOH, I'm just being very careful to not dump this on my fingers. NaOH, it ends with hydroxide, ends with OH. That's the Arrhenius definition of a base. It produces OH minus in solution. And so if it starts with H, we would classify it as an acid. That's following the Arrhenius definition. If it ends in OH, it's a base according to the Arrhenius definition. In a little bit, we'll look at the Bronsted-Lowry definition and look more at conjugate acids and conjugate bases. So what I want to do is I want to just kind of review litmus paper, pH paper. So I have a vial of red litmus paper. I have a vial of blue litmus paper. So litmus paper is just a piece of paper that either turns red or blue. So this is a piece of red litmus paper. Acids turn litmus paper red. Whether it's blue or red paper, if it turns red or if it stays red, it's an acid. So for example, if I dip this into HCl, right, the red paper stays red. So if I didn't know what this was, right, that kind of helps me, right? NaOH, so see how it's turning kind of a purple color. Right, we would say that that's turning blue. Bases turn litmus paper blue. I could do the same thing with blue paper. So with blue litmus paper, right, so a piece of blue litmus paper, if I dip it in an unknown solution and it stays blue, that tells me that it's a base. If I dip this into an acid and it turns red, that tells us that it's an acid. Now that's really all litmus paper can do. Based on the color that it turns, right, and if I actually, let me scoot this up really quick, you can see the paper. Right, see how the blue paper turned red, the red paper turned blue. Just think about B for base, B for blue. If litmus paper turns blue, it's a base. That's all that litmus paper can tell us. We also have pH paper. So pH paper comes in a vial and it has these different colors that tell us approximate pHs. So with the pH paper, I'm going to rip it in half to save my fingers. So what I can do with the pH paper is I'll dip it into the acid. See, it turns this pink color. Well, what I can do is I can compare it to the colors on the vial. So this is closest to a pH of 2. Now, is that an exact pH? No, but it tells me that it's a low pH. Low pH is an acid. Do the same thing with the base. So I dipped it into the base, compare it, right? I notice that it's closest to pH of 10. That tells me that it should be a base. Now, one other thing I'm going to pour some of the NaOH into this little beaker. We're going to talk more about acid-base indicators later, but one of the indicators, so an indicator changes color based on whether it's an acid or a base, and every indicator is different. So I have this indicator, right, which is called phenolphthalein. It is many letters that all don't make sense when together. So the indicator is called phenolphthalein. The importance of phenolphthalein is that it turns pink in the presence of a base. So if I add some phenolphthalein to this beaker that I added NaOH to, it turns pink. An indicator, litmus paper is also an indicator. It helps us indicate whether we have an acid or a base. So if we have an unknown substance, actually it was HCl. I wasn't sure if it was HCl or not because it was in a container next to the HCl but wasn't labeled. So I actually just took a piece of pH paper and litmus paper and I tested to see if it was an acid. It was an acid, so I was like, okay, should be the excess HCl. So phenolphthalein, right, is another indicator that tells us if we have a base. Now, if I put phenolphthalein into the HCl, it doesn't turn colors because it actually only changes color at a certain pH. I want to look at a couple things from the video. So one of them was looking at strengths of acids and bases. Now this kind of diagram that was in the notes is going to be useful because what this shows is strong acids, strong bases. And we're going to use it as we talk about what is stronger, right? What acid and what base is stronger. So something to keep in mind, strong acids are completely dissociated in water. HCl, HBr, HI, HNO3, H2SO4, HClO3, and HClO4. Those are your strong acids. They completely ionize, they break apart completely in water. They're conjugate bases. So their pair, right, their opposite, is neutral. We're going to talk more about these pairs, but something that we have to keep in mind is that we have one of two pairings. We either have a pair that is strong and neutral, or that is weak and weak. Those are our two options. Strong and neutral go together, or weak and weak go together. So weak acids, we'll talk way more about weak acids and weak bases next week. They only partially ionize in water. And so their conjugate bases are also weak. So we either have strong neutral or weak and weak. Now, if we have a substance with negligible acidity, negligible means insignificant. So negligible acidity means it's neutral. So if we have a substance that's neutral, right, it's not going to dissociate. Well, their conjugate base is strong. So notice we have neutral, strong. So we have one of two pairing, strong and neutral or weak and weak. We're going to keep looking at this as we go through examples. I already talked about that. Again, strong and neutral or weak and weak. Now, when we are looking at acid-base reactions, we are going to tie it back to equilibrium. So equilibrium will favor the reaction that moves the proton to the stronger base. Here's what this is saying. This is saying that the stronger base will act as the reactant. So whichever base is the stronger base will act as the reactant. So in this example, and again, we're going to look at labeling the conjugate acids and conjugate bases, but H2O, right? You always have an acid and a base on each side of the arrow. You have an acid and a base on each side of the arrow. Looking at this, water is the base on the left, Cl- is the base on the right. H2O is actually a stronger base than Cl-, because Cl- actually comes from a strong acid, so Cl- is neutral. So since H2O is a stronger base than Cl-, H2O will act as the reactant. meaning HCl and H2O are the reactants, forms products. So we would say equilibrium lies to the right. That means HCl and H2O are the reactants, H3O plus, Cl minus are the products. If it were the other way, if Cl minus were stronger, that means that H3O plus and Cl minus will act as the reactants, and it would favor the left side. So the stronger base will always act as the reactant in an acid-base reaction, and they are always at equilibrium. So we should see a double arrow here. Right? These exist at equilibrium. So let's look at example 1. Right? And example 1 starts on page 15 of the notes. So with example 1, for the dissolution of HNO3 in water, the dissolution, that means that HNO3 is breaking apart. For the dissolution of HNO3 in water represented below, which species are Bronsted-Lowry acids, bases? We're going to look at conjugate acid-base pairs, and what occurs that identifies it as an acid-base reaction. So, College Board uses the Bronsted-Lowry definition of acids and bases much more than the Arrhenius definition. When we are given a reaction that looks like this, before you do anything else, look at the left side and look at the right side. Look and see what has to happen to get from what we have on the left to what we have on the right. So for example, if I look at this, I say, okay, we have HNO3 plus H2O. What forms NO3 minus? And H3O plus. So I notice that HNO3 becomes NO3 minus. Then you ask yourself, well, what does HNO3 have to do to become NO3 minus? Well, HNO3 has to give up its proton, give up its H plus. When we talk about protons, we're going to be talking about H plus. So HNO3 has to give up its H plus. Because think about it, HNO3 becomes NO3 minus. If it gives up an H plus, it's not only giving up an H, but it's also giving up that plus charge, which is why it becomes minus. So HNO3 is donating an H plus. Something else has to accept it. You can't have one without the other. HNO3 is donating the H plus. H2O is accepting the H plus. The Bronsted-Lowry definition of an acid is a proton donor. A Bronsted-Lowry acid is an H plus donor. A Bronsted-Lowry base is an H plus acceptor. So if I'm labeling, I see that HNO3 is donating an H plus. That would make this an acid. H2O is accepting the H plus. That makes it the base. You always have an acid and a base on each side of the arrow. But what we're going to have on the right side are what are called the conjugate acids and bases. Conjugates are what we get after making changes to what we have on the left side. So HNO3 acts as my acid. Once HNO3 loses the H plus, it becomes NO3 minus. NO3 minus is called the conjugate base. So I always label CB for conjugate base. The conjugate base is what is produced after the acid loses the H plus. So you still have an acid, you actually have an acid-base pair on the left, you'll have an acid-base pair on the right, and you'll have an acid conjugate base pair on opposite sides of the arrow. then water accepts the H+. So it's a proton acceptor. After it accepts the H+, it becomes H3O+. So after the base accepts the proton, it becomes the conjugate acid. Notice how the acid and conjugate base and the base and conjugate acid differ by an H+. So the Bronsted-Lowry acids, you're going to have one on each side. It's going to be HNO3. That's the acid that's on the left. The acid that's on the right, even though it's labeled as a conjugate, it still would act as an acid. Because if the reverse reaction happened, H3O+ would donate its proton to NO3-. So the two acids are on opposite sides of the arrows, HNO3 and H3O+. The Bronsted-Lowry bases, so these are what accept the protons. So we have H2O, and then the conjugate base on the other side of the arrow is NO3-. Because if we looked at the opposite reaction happening, so let's say instead of going left to right, it went right to left. Well, to get from H3O+ to H2O, H3O+ would need to donate one of its H+. So that's why it acts as an acid, and NO3- would act as a base. So then part C, what are the two sets of conjugate acid-base pairs? So we have HNO3 and NO3- and H2O, H3O+. Notice again how they both differ by just one H+. And then part D, what occurs during the reaction that identifies it as an acid-base reaction? The H+ transfer. A proton transfer tells us it's an acid-base reaction. When H+ is transferred from one substance to another, it's going to be an acid-base reaction. We use the Bronsted-Lowry definition more than anything else. Questions on example 1. So let's look at example 2. And so we're going to do the first one together. I'm going to see if you guys can do B and C on your own, and then we'll check answers. So again, this is designating the Bronsted-Lowry acid, Bronsted-Lowry base, and then the conjugate acid, conjugate base. So just like what we did before. The first thing that you want to always do, look from the left to the right. Label what is happening from the left to the right. I like looking at the opposite side. Look for what is similar. I see NH4 plus and NH3, and I see Cn minus and HCN. So I'm going to say, okay, what has to happen to get from NH4 plus to NH3? Well, NH4 plus would need to donate one of its H pluses. NH4 plus is going to donate one of its H pluses to Cn minus. Then what happens is then it becomes NH3, and Cn minus becomes HCN, because you're adding an H and a plus 1. So if NH4 plus is donating the proton, it is the acid. Cn minus is accepting the proton, it is the base. After NH4 plus gives up its proton, it becomes NH3. So if NH4 plus is the acid, NH3, after it loses the proton, becomes the conjugate base. So see, you have an acid conjugate base pair. After Cn minus accepts the proton, becomes HCN, which is the conjugate acid. So I just want to point out really quick how this differs a little bit from the Arrhenius definition. The Arrhenius definition says but a base needs to have OH minus. Well, CN minus acts as a base here, but it doesn't have OH minus. So the Arrhenius definition has some limitations. Right? The Bronsted-Lowry definition just focuses on donating an H plus or accepting an H plus. So see if you can work through B and C. Label the acid, the base, and then on the opposite side, the conjugate acid and the conjugate base. Remember, you should have essentially 3 acid-base pairs. You can have an acid and a base on the left, an acid and a base on the right, and then across the arrow, you're going to have an acid-base pair, the substances that look similar. Okay, so you can check for B and C. So in B, water is actually the acid, because if you look from the left to the right, it goes from H2O to OH minus, so it has to lose an H plus. And then across the arrow, if H2O is the acid, OH minus is the conjugate base. In part C, so I want to point something out in part C. So HCHO2 is the acid, PO43 minus is the base. Notice how PO43 minus is only accepting one H plus. It goes from PO43 minus to HPO42 minus because you're adding an H and a plus because it's H plus. So you're adding an H and a plus 1 to the charge. The acid base, like the conjugate acid base pairs, only differ by one H plus. So it doesn't go from PO43 minus to H3PO4. They only differ by one H plus. Any other questions on the conjugate acid base pairs for now? Yeah.
The atoms with, or molecules, the acid molecules with stronger charges tend to dissociate less easy?
So we'll talk more about, those are called polyprotic acids. And yes, so most polyprotic acids are weak acids because they have to ionize into 3 separate hydrogens, with the exception of H2SO4, because H2SO4 is a strong acid. But yeah, usually polyprotic acids are weak acids, so they'll only, if they ionize, they'll only ionize into one, like H. So for example, for H3PO4, would ionize into H plus and H2PO4 minus. Okay. Yeah. All right, so example 3. We're gonna look at an amphoteric substance. So we're still dealing with the Bronsted-Lowry definition, but we're gonna talk about what it means to be amphoteric. So the hydrogen oxalate ion, which is HC2O4 minus, is amphoteric. Amphoteric means it can act as an acid or as a base. Water is another common example of an amphoteric substance. So amphoteric substances have the ability to either donate an H, so here is the H plus that it could donate, but usually if it has a negative charge, or if it has lone pairs, it can also accept an H, which is why H2O can act as an amphoteric substance. So in part A, it wants us to write a balanced equation showing how this ion can act as an acid toward water, and another equation showing how it acts as a base towards water. And then we'll actually answer part B kind of within part A. So I'm going to show 2 equations. I'm going to show it acting as an acid, and I'm going to show it acting as a base. So the hydrogen oxalate ion, HC2O4 minus, and in both of these we're showing how it acts toward water. And I'm putting the double arrow because most acid-base reactions, unless it's a strong acid or strong base, will exist at equilibrium. So in this first one, if HC2O4 minus is acting as an acid, what is it going to do with the proton? Donate or accept?
Donate.
Donate. Right? An acid donates its H plus to the other substance. So here, It's acting as an acid, meaning water is accepting, acting as the base. Well, when the hydrogen oxalate ion loses its H+, it's going to become C2O4. It's losing an H, but it's also losing a +1. So subtract 1 from the charge. So the hydrogen oxalate ion, when it loses the H+, becomes oxalate, the oxalate polyatomic ion. And then when water accepts the proton, we're adding an H, and we're adding 1 to the charge. Becomes H3O+. It's called the hydronium ion. So then if we label everything, hydrogen oxalate is the acid. After it loses the H+ and becomes oxalate, oxalate is the conjugate base. After water accepts the proton and becomes hydronium, that's the conjugate acid. Then we look at how it acts as a base toward water. So now if it's a base, what is it doing with a proton? If donated as an acid, it's going to accept as a base. So if it acts as a base, it's accepting a proton, which means water is donating the proton. Proton has to come from somewhere. You can't have an acid without a base. So after hydrogen oxalate accepts a proton from water, we're adding an H, so H2, C2O4, and you're adding 1 to the charge. So it becomes neutral, becomes oxalic acid. And then after water donates a proton, it loses an H and a +1, becomes OH-. So after hydrogen oxalate accepts a proton, it becomes oxalic acid, which is the conjugate acid. After water donates the proton, it becomes hydroxide, which is the conjugate base. This is why, right, even though it doesn't have, well, it technically has hydroxide in it, but it produces hydroxide, and hydroxide is a very strong base. So then part B, what is the conjugate acid and base? Well, see, we did it right here. Here's part B. There's part B. So by answering part A, we were able to answer part B as well. So again, this is just showing how a substance can be amphoteric or amphoprotic. Those are the same terms. When it can either accept or donate a proton, whether it's acting as a base or as an acid. Questions on this one? Okay, now we get to do math. So the last 2 examples, we're going to look at some math. On your equation sheet, I do want to point out on the front page under equilibrium. So we didn't really use the equation sheet much on the last unit because the equation sheet had Kc and Kp, but we were able to write the K expressions. So on the equilibrium, or on the equilibrium portion of the equation sheet, we also underneath that see Ka and Kb, which we'll get to next week, and Kw. And it says Kw equals H plus times OH minus equals 1 times 10 to the negative 14 at 25 degrees Celsius. So Kw relates the H plus and the OH minus concentrations. So in example 4, it says calculate the values of H plus concentration and OH minus concentration in a neutral solution. So I'm going to point out a couple things. Thing number 1, the definition of a neutral solution is not necessarily what most people think. A neutral solution. Neutral means the concentration of H plus equals the concentration of OH minus. There were some questions on the video that said, well, if an acid has a pH below 7 and a base has a pH above 7, what has a pH of 7? And usually our answer is a neutral solution. But that is assuming that we're at 25 degrees Celsius. We're not even at 25 degrees Celsius in this room, usually. So our neutral solution is not, or our neutral pH is not actually 7. So it's important to remember that a neutral solution has the H plus and the OH minus concentration equaling. That's the definition of a neutral solution. So when we want to calculate H plus or OH minus, we want to use KW. KW relates these two variables, H plus and OH minus. So KW equals H plus times OH minus. And we know that KW at 25 degrees Celsius is 1 times 10 to the negative 14. Now, you might look at this and say, okay, well, we have to calculate both of these and all we have is one value. Yes, but a neutral solution, the two are equal. The two are equal. So I could use any variable. If H plus is X, then so is OH minus. Or you could just plug in and I could say, well, I know that H plus equals OH minus, so I could do H plus squared. Right? Those two variables are equal because it's a neutral solution. Right. Here's how we can actually do this without a calculator, practicing our mental math. What do I do to solve for X?
Square root.
Square root. Right? Taking the square root is the same as taking something to the 1/2 power. Here's how we can do it without a calculator. What's the square root of 1? 1. Now, to do this without a calculator, multiply these two. What's half of 14? 7. So half of negative 14, negative 7. So I guess I'll add my little molarity unit. At 25 degrees Celsius, in a neutral solution, the H plus concentration and the OH minus concentration are equal to 1 times 10 to the negative 7th molar. So the importance of this example is the idea that a neutral solution, H plus and OH minus, are equal. So then for example 5, now we're not going to be at a neutral solution anymore. Example 5, we're calculating the concentration of H plus. So we have two examples here. Calculate the concentration of H plus, part A, in which OH minus equals 0.01 molar, and part B, a solution in which OH minus equals 1.8 times 10 to the negative 9. On your equation sheet, you always have KW. Notice it says, unless stated otherwise, assume the temperature is 25 degrees. Otherwise, we can't use the KW comparison. Or they would have to give us a new KW. So if I look at part A, I know that KW, which is 1 times 10 to the negative 14, equals H plus times the concentration of OH minus. In this case is 0.01 molar. So I can solve. So 1 e negative 14 divided by 0.01. H plus concentration is 1 times 10 to the negative 12. Don't forget that brackets means molarity. KW is a capital K. It's an equilibrium constant. It's the equilibrium constant for water, right? For the ionization of water. In the KW expression, the reason that it's just H plus times OH minus is because water is a liquid. We're still talking about equilibrium. Liquids are not included. That's why it's not H plus times OH minus over water. It's just H plus times OH minus equals this constant. So KW does not have units, but concentrations will have units. So part B, see if you can plug it into your calculator. Solve for part B. We're solving for H plus when OH minus is 1.8 times 10 to the negative 9th. So I got 5.56 times 10 to the negative 6th. Very last thing that it wants us to do is specify whether the solution is acidic or basic. Acidic means that there's more H plus. Basic, more OH minus. So if H plus is greater, it's acidic. If OH minus is greater, it's basic. So here, OH minus is 0.01. This is 1 times 10 to the negative 12. In part A, OH minus is a greater number. So in A, it's basic. Part B, a little more difficult. Compare the exponents. Negative 6 is greater than negative 9. So part B is acidic.